good. You know, CSC548 with a little bit of home association trick.
That's right. Okay, so we had a paper on one's complement and two's complement. All right, so tell me about these guys. What's the point of both of those guys, and what's good about them, what's bad about them, pros and cons?
Well, one's complement just kind of reverses the bit.
Okay.
And then that goes from negative 127 to 127, and it has two values for 0.
Okay, so one's complement. So reverses all bits. So all of these are negative number representations, right? That's the point of these guys, okay? So this reverses all bits. What are the pros of one's complement? What's good about it?
As opposed to just having one bit that determines the sign, like addition actually works.
Okay.
Like if you just have one bit for the sign, then adding doesn't.
But that's not one's complement. That's
Right,
sign and magnitude.
Like addition actually works on it.
On one's complement?
Yeah.
Okay.
As a method for determining negative numbers.
Okay. But really, I mean, the biggest benefit of one's complement is that it's easy. It's easy, right? Flip all the bits, done. Okay, so this guy's easy. What about con?
Two values for 0.
Yeah, two zeros. So we have a negative 0 and a positive 0. Two zeros. Say this again?
To process that negative 0 and to work on that overflow, we need an extra circuit. So we came up with the two's complement.
Okay, so now we're talking about two's complement, okay? So here, let's actually do this all in one line. Cons, 2 zeros. So two's complement reverses bits and adds 1. Okay. What are the pros of this? Okay, so fast subtraction. If we're comparing it to the ones complement, 1 0. We get away with 1 0 for this guy. What about con? No legendary orange. So leave con out for right now. Any other negative number representations you guys came across as you were
There's the
sign and magnitude? Okay.
But what I read was two's complement kind of became the standard.
Okay. Well, how does sign and magnitude work?
I didn't really read about it. One bit means it's positive or negative. I know. And the other bits determine how large.
The rest are value. Okay. And which one is, so a 1 is what? Negative or positive? Yep. And a 0 is positive. Okay. Is the same thing true with two's complements for those values? 1 and 0? Except for those, instead of choosing it, it happens to become it mathematically, right? So let's look at a one's complement example here. So we'll use a small number set just so we don't have too many of them. So let's look at 3-bit numbers. All right. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. All right, so those are our number system containing 3 bits, right? Okay, so for this guy, now one thing we mentioned this earlier today in the 325 class is kind of an important thing that we want to start thinking about here is that our number systems aren't always mathematical. When we have series of bits, sometimes those bits just represent a value. And it doesn't always have to be mathematically solvable. All right, that doesn't, I mean, many times it is, but it doesn't have to be. All right, so we're really trying to say this pattern represents this value. All right, so if we're just looking at positive numbers here, this is a 0, this is a 1, this is a 2, copy that. That's a 3. Okay, so let's just stop there for a second. So if I want to represent, if I want to have a 3-bit number system, and I want to represent positive and negative numbers, right off the bat, we know that one of those bits are going to be used for sign. Whether it's 1's complement, 2's complement, or sign and magnitude, we're giving up a bit to store sign, correct? Okay, so with a 3-bit number system, we really have 2 of those bits to represent our values. So this is really a base 4 number, a base 4 signed number system that we're looking at here, right? So 0 to 3 would be a base 4 number, and then all of these guys are positive numbers because they have 0 in front of it. Now, if we look at sign and magnitude, well, actually we're doing 1's complement here. All right, so 1's complement says we're going to flip these bits. So this is actually 0, 1, 1. Hold on, I'm going backwards here. So if we do this as 1's complement, we're actually starting with negative numbers.
Like, nothing's happening.
I mean, nothing's happening. Oh, you don't see stuff typing on the screen?
No.
Oh, there it is.
What the?
You
Okay.
can't see him type spaces.
Is that what?
No, he said type spaces.
Oh, I think I was probably just circling stuff. Can you not see that?
No, we can't now. You weren't a minute ago.
Really?
No, it wasn't.
Sometimes I'm a ninja. It happens. All right, so actually let me
I
do
feel like
this.
you'd be more, you'd fit in better at the sumo wrestlers. But that's just me.
I'm actually going to do this in a spreadsheet. I think that'll look better.
Them.
Well, this is going to be crap anyways because it's going to turn everything into numbers. So I guess we're sticking with this.
It's just a really quick switch.
Yeah, I know, to make it a text, but I gave up on it. I mean, it's okay. I have a legendary belt. So basically, I never run out of mana. That's what it comes down to. It's the thing. All right. So if I'm looking at the 2's complement of this, and actually, here's a good way to pull this off. So I'm going to take this. Let's get rid of these guys here. All right, so those are our initial values. Now the 1's complement of these guys, so if we're storing it in a signed number system, this would be 111, 110, 101, 100, 011, 010, 001, 000, like that. Okay? So this is turning every one of these numbers into their 1's complement equivalent. Now we need to assign values to these to see how do we represent our negative numbers using this system. So I'm going to steal this guy. All right, so we're going to call this guy -0. This guy is, how do I want to do this? Is this even going to look right when it's done? Let's just go with it. -1, -2, -3, +3, 2, 1, 0. All right. So we have to know that all these guys are in one's complement format, right? We know that that's how they're encoded. Therefore, we know that we're dealing with signed numbers. So since these guys are encoded in one's complement, we're assigning the value of -0 to this guy, -1 to this guy, -2 to this guy, and so on and so forth. And as we already pointed out, one of the weaknesses of one's complement is we have 2 zeros. We're representing 0 2 different times. A -0 and a +0, who cares if it's positive or negative, but it's twice, right? All right, so now when we get to the positive numbers, so this is a 0 here means that it's a positive number, right? So the first sign bit is it's positive. So this is a 1 in the ones place and a 1 in the twos place, so this is a +3. This is a +2, a +1, and a +0. Okay, now when we get back up here, we see that the things actually map, I guess, well, let's walk it the other direction because we can, it's broken either way, but we'll assign it this way. So let's make this guy -0. This guy is going to be -2, no, -1, -2, -3. That's correct. All right, so we have 2 negative values, or 2 zeros rather, and everything walking down this way is positive, 3, 2, 1, 0. Everything walking up is negative, -1, -2, -3. And the real issue here is, and this kind of goes back to what I was saying before, is if we think about these as representative patterns, we have 2 separate patterns that both map to the same value. That's potentially problematic from a logic perspective, but it's even more problematic from an implementation perspective. Okay, so we're implementing that in hardware. It's going to be kind of difficult to have 2 different input patterns that map to the same output. All right, so we're going to say one's complement is weak from that perspective. Okay, now let's take this exact same slide and let's call this guy sign and magnitude. Okay, so sign and magnitude. Let's dump this guy. So we're going to have all of our so 0, 0, 0, 1, 1, 0. Okay, so we're going to just steal these values here and paste them here and change all of these guys to ones. All right, so with sign and magnitude, we're not flipping any bits. All we're doing is we're saying a 3-bit number, one of those bits is used to represent sign. All the other bits are used to represent magnitude, value. All right, so this is a 2-bit system then. So we have 0. So let's go ahead and move these guys in here. So this is 0. This is 1. This is 2. This is 3. This is -0. This is -1. This is -2. This is -3. All right, so exact same issues we had with one's complement. We have 2 zeros, but both of these guys map. Difference is that we didn't have to flip any bits. So if we had to compare sign and magnitude to one's complement, which would you pick? Okay, why? But ones and sign and magnitude both have 2 zeros. Okay, why?
You don't have to take the time off looking.
So one of
If you're comparing between the two.
okay, so one of the things that should have come up in your paper is probably that 2's complement is almost universally accepted as the way to model negative numbers in a binary mapping today, right? And its competitor, really the guy he's against, isn't 1's complement. The guy he's against is sine and magnitude. So what makes sine and magnitude a better than 1's complement? Let's go here. That way we can get them sitting next to each other. All right. So these are our sine and magnitude. These are our 1's complement. Is one better or worse than the other?
Same, but one.
They all
Science
map to the
magnitude
exact
seems to be like
Huh?
in order, right? How they're all mapping to the exact same thing.
Okay. So this guy is this guy is numerically created, right? With just bits being, so we've arbitrarily put 1s in front of all these guys for the sine. Arbitrarily put 0s in front of all these guys for the sine. So this is positive numbers, these are our negative numbers. But these 2-bit mappings, these are all math, right? This is just counting. 0 to 3 in 2-bit counting. Over here, we're not really counting. Right? We actually flipped the bits, and it just so happens that it works out that we can count backwards and then count upwards. But we still are treating this guy as a negative. So the outcome is the same, but the way we got to the outcome is different. So we might ask, why flip the bits if we didn't have to? That might be a reasonable way of looking at it, because he said they all map to the same thing anyways. Got to the same result 2 different ways. All right, but we're going to say that the weakness with both of these guys is the 2 zeros, right? Okay, so let's dump this here. Let's copy this slide. Let's go to this. Let's look at this as a 2's complement. Okay. So 2's complement, and we're going to come back and talk about carry flag as well, because that when we actually start doing math with these guys, things get a little wonky. All right, so 2's complement uses 1's complement as an intermediate step, right? All right, then we add 1 to that guy. So if we add 1 to 1, 1, 1, 1, or 1, 1, 1, what do we get? So 1 plus 1 is, so let's just look at the math here real quick just so we can. So this is 1, 1, 1, and adding 1 to it. So 1 plus 1 is 0, carry the 1. So we have an extra carry 1 up here. One plus 0 is 0, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. So here is the 2's complement version of the 1's complement 1, 1, 1. But we have a carry bit here. That make sense? All right. So this guy would map to 0, 0, 0. This guy maps to 1, 1, 1. This guy maps to 1, 1, 0. This guy maps to 1, 0, 1. This guy maps to 1, 0, 0. 0, 1, 1. 0, 1, 0. And 0, 0, 1. That look right? All right. So this is the 2's complement mapping. Right off the bat, one advantage we should see is we only have one thing that looks like it's going to represent a 0. Are these all unique? Okay. So let's assign values. So that's 0. Now a 1 means a negative number. So this is a negative 3. This is a -2. This is a -1. What's this guy? This guy? Three, two, one, like that. All right. So right off the bat, we have, well, right off the bat, we notice we only have 1, 0, rather than having two separate things mapped to 0. But we have this brand new number that we're able to represent. So when we've seen, when you introduce programming languages and we talk about, like in Java, how a 16-bit value can hold values in the range, well, let's do bytes. A signed byte can hold values in the range of -128 to +127. Remember that? For 8 bits? And now we're looking at 3 bits, a 3-bit number. So the 3-bit number can hold, a signed 3-bit number can hold values in the range of -4 to +3. Make sense? That's why that negative value is 1 larger. So there's your evidence that we use 2's complement as the kind of the consistent form. Rather than getting a duplicate, we get 1 extra value that we can represent. Make sense? Okay, so that's our 2's complement numbering system. Now, explain to me, why is this a -4? That was our one outlier, right? All the other ones, we got the value from these guys here. So we look at that 1 there, and that's the sign. Why is this one a -4 when all the other ones, that one didn't, the bit didn't have a play in it? Don't all speak at once. We wrote big papers on this, right? It's fine. So what's wrong with it?
-1 would be 111.
So you had -1 is 111?
Yeah.
Okay.
So it doesn't use bit.
Ah, hold on. So let's get his mapping up. So you had this 111 as -1.
Yes.
Okay. Keep going.
-2, 101 is -3, and 100 is -4.
100 is -4. Okay, fair enough.
No, that's forget.
Okay. So, fine, we'll use this system. What makes this guy -4? What makes this guy -3? This is 0. That one's easy, right? Okay. This one we have a -1. Why is this? Why is 111 -1? Well, the 1 here, we can say, well, that's -1 because of the 1. It's negative, rather, because of the 1. What about the rest of it? Why is this a 1?
It's the opposite. The 1-1 is the opposite of. Would that be 1-1-1? It should be 1-1-0, right?
Oh, I mean, these are just out of order.
Okay,
Yeah, it's fine. They map to the right stuff.
yeah. Okay.
So a few minutes ago, I said something like, these things don't always mathematically make sense. We sometimes use patterns to represent values. What can you tell me about all these values? Are these just flat out numbers, or are they encoded in some way? Specifically, how are they encoded? In 2's complement. So what does 2's complement mean? When we encode a value in 2's complement, what does that mean? How do we reverse 2's complement? If I'm looking at this value right here.
Subtract 1 and then take the inverse.
Okay, so I know that this guy right here is a negative number. If I know all of these are 2's complement values, I know that they must be mapped. Well, the reason I put them in 2's complement is to give me the sign bit, right? So these are all negatives. Here's my positives. So our positives out of order here. All right, or our non-negative, since we have a 0 as non-negative. Once I get the sign, in order to get the value out of it, what do I need to do? I want to get the 1 out of 1, 1. So if I come back here, we'll just call this scratch space. All right, so I have 1, 1 here. So we know that this guy is in 2's complement form, correct? So first thing I need to do to get it out of 2's complement form, and actually here we'll do the whole number because technically the whole number is in 2's complement form. So the very first thing I need to do to get it out of 2's complement form is to bring it into 1's complement form. Okay, how do I do that? Subtract 1. So that's 1, 1, 0. Now we're to that. Okay, now I need to get it back to its original form. 0, 0, 1. There's our 1. So we know it's a negative number because in 2's complement form, it's a value of 1 there. But then the value, the magnitude, if you will, that comes after the sign is the original value that this guy mapped from. Make sense? Let's try it on this one. 1, 1, 0. Okay, we're saying that this guy is a negative 2. Why is it negative? Because we know this is in 2's complement form, and the far left, the most significant bit, is a 1. So it's a negative number. Fine. So now we need to subtract 1 from 1, 1, 0. And how do I do that? How do I subtract 1 from a value? We can do this in decimal, right? We can just convert it real quick in our head and do it. But if I had a binary number like this and I wanted to subtract 1 from it,
Well, you go to the end. If it's odd, you just take that 1 off. And then, but when you even, you have to take it the 1 from the even or the 2 spot. You can change that to 0 and then change it to 1 for that. Take the 2's complement and then add it.
so you want to take the 2's complement of this guy.
Yeah.
Okay, fair enough. So that is 1, 1, 0 plus 1, like that. And then you add it. So this is, let me just get my base here. So this is 1. This is 0 with a carry. This is 1 with a carry. Right? 1, here, let me give you the carry bit again, just so you can see that. So this is the value we're hoping it turns into. So 0 plus 1 is 1 with no carry. 1 plus 1 is 0 with a carry. 1 plus 1 plus 1 is 1 with a carry. So when you get a 3 is a 1 with a carry. Power of 2. All right? So we have a 1 as a carry bit here. So subtraction of 1, 1, 0 minus 1 gives us 1, 0, 1. Okay, so that gets us, so from here, we subtracted 1 from it. That gives us 1, 0, 1. Then we flip the bits. 0, 1, 0. And that's the value 2. Make sense? All right, so we knew it was a negative number from its encoded most significant bit. Then we had to get what's the magnitude by decoding it out of 2's complement form. All right, make sense how that works? All right, so we have a number representation system that isn't necessarily based on math. Happens to work out as math, but it's not necessarily based on math. Okay? We picked patterns, and we assign things to the patterns. And as long as we use the encoding to give us the sign, and then the decoded value to give us the magnitude, we get rid of the problems of having a small number and a large number. So now let's look, just as that extra little one here, the -4, which is 100. So we're hoping this guy turns into a -4. There's our 100. We want to subtract 1 from 100. So that is then add these guys together. So that is going to be 1, that is going to be 1, and that is going to be 0. Carry the 1. Do that right? 100. Oh, I need to flip the bits first, then subtract. No, subtract 1 first. All right, so we're going to flip the bits on this guy. 1, 1, 0. Then we're going to add 1 to it. So that's the 2's complement version of, what's not?
It should be 0, 1, 1.
I want to subtract 1 from this guy. So that's the number 1. So instead, we want to be able to add these guys together, right? So in order to do that, we need to flip all the bits on this guy. So that's 1, 1, 0. And I need to add 1 to that. So this is the 2's complement of,
That's right. Yeah,
of 1.
Yeah. It'd be 1, 1, 1 with the carry bit.
So 1, 1, 0. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 0. Carry the 1. So this is a carry, right? All right. So this is our magnitude. So what's up with this? We had it work for -2. We could assume it would have worked for -3, right? So -2, we had 1, 1, 0. So this is our 1. So we'll add 1 to it. Do we see the issue yet?
That is the maximum number from the leftmost side, right? If you use the n bit register, like 3 bits, you said, and that is the maximum leftmost number you can get.
What's this value right here?
That says mathematical
Oh,
3.
no.
but it doesn't
What does this value represent?
the decimal.
I just took a 2's complement number and I subtracted 1 from it. So if I take a 2's complement number and I subtract 1 from it, what does that give me? A 1's complement number. How do I get the number? Flip the bits. So this is 1, 0, 0. Isn't that our 4? That's where we get the -4. Make sense? So that's where we get the extra value on the negative side. So things that are 8 bits, -128 to +127, 16 bits, -32,768 to +32,767. The difference? 32 bits is -2 billion and blah, 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 to +2 billion and blah, blah, blah.
2 billion, 100 million something, right? 2 billion, 100 million, 700. It's 217 something.
I don't know. Plus or minus, well, I mean, here, this is what it is. It's 2 to the 31st power. So it's 2, 2,147,483,648 to, that's negative, to 2,147,483,647. That's the range. And then if you want to do this for 64-bit, it's that.
Yikes.
That's the negative, and then the positive is that -1. All right, make some sense? All right, so we're able to encode values in the positive and negative, and what we gain in 2's complement is A, we don't have duplications, and B, we're able to store an extra value. Now, we might say, well, that doesn't make a whole lot of sense. We get this extra value now. Well, why can't we have the 4 on the positive side? Well, we don't have the registers for it. The math doesn't work out that way. Really, the reason the 2's complement is what has been widely accepted is because it's the one that can be implemented in hardware. Now, that doesn't mean we couldn't implement either of the other 2 in hardware, but what would why would it be difficult? Hopefully this came up in some of your papers. Why would it be difficult to implement either sign and magnitude or 1's complement? Specifically sign and magnitude. Why would it be difficult to implement that in hardware? But
Because when you add the positive to its negative, you don't get the 0. When you're adding a positive number to a negative number, when you do binary addition, it doesn't return the correct value.
okay, so we take this guy right here. If we take 3 and add to it -3, we should get a 0. Okay, so our 3 is 0, 1, 1. 0, 1, 1. Our negative, I'm on the wrong screen here. Our -3 is 1, 1, 1. Already got it. We want to add those guys together. Here's our carry bit. 1 plus 1 is, let me give myself several zeros here. That's 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 1 plus 0 is 0, carry the 1. So this gives us a value of 2, when this should have given us a value of 0. We were hoping this would give us a 0. Right? 3 plus -3 should be 0. Got a couple of math guys in here. That sound legit? All right. Okay. All right. So let's look at -3 and 3 in 2's complement. So -3, 1, 0, 1. 3 is 0, 1, 1. 1, 0, 1. 0, 1, 1. Add these guys together. This is 0, carry the 1. 0, carry the 1. 0, carry the 1. We have a carry bit. Is that guy 0? Seems to test out. All right, so certainly we have an accuracy issue. All right, so that is, so the question I asked, which we're most of the way down the path, but let's just make sure we're clear on why it's difficult, was why is it difficult to implement the 1's complement or the sign and magnitude in hardware? It wouldn't be impossible, would it? I mean, hey, with enough solder and enough wires, we can make anything work. Well, anything, I guess. But most things would be in the realm of possible. Why wouldn't we do this?
Because it's not practical.
Okay, in what way?
You could make it work, but there's a much better way to do something.
Okay, but what makes it better when we look at it from a hardware level? Now we're right back to the argument of space and heat. Would sign and magnitude take up more physical space to implement it to be right? Because there's a whole bunch of like kind of exceptions, right? So we have more stuff, which more stuff equals more space equals more heat, equals more power draw, equals more, whatever. More is bad. If we could have the equivalent solution with less. Kind of make sense? So from an accuracy perspective, either one of them works. I mean, we can make the mappings. But 2's complement, we can apply the exact pattern every single time and get a consistent output. So we only have to create the circuit, if you will, for that pattern. And realistically, do you think they create the circuit for that pattern, or do they create the circuit for portions of that pattern? What goes into 2's complement? 2's complement is a flipping of the bits, right? What does it mean to flip the bits? What Okay, you got it. What did you say? A not. So if we think about this in terms of, a high-level language like Java, if we do not true, we get a false. If we do not false, we get a true. That flips a bit. So if we not an entire number, so now we're getting into like assembly instructions. So the not instruction, if I do not 1, 1, 1, the result of that would be 0, 0, 0. So it does a bitwise not. For each bit, it flips it to the opposite bit. All right, so is that one of the moving parts of 2's complement? Is this instruction gives us part 1 of 2's complement? This is really not is synonymous with 1's complement, right? Flip the bits. All right, and then what do? We add 1 to it. Probably is an add command, right? Probably read about it in the tutorial or something like that. But yeah, so we can add crap. So it's not that the 2's complement circuit exists. It's that the individual mechanics that go into making a 2's complement are built into the assembly language, the 8086 assembly language. That make sense? Now, what if we tried to do this with sign and magnitude? What if we tried to write an assembly language program for sign and magnitude? Wouldn't there be a whole lot of complexities there to make things map out to the right place? Where things kind of just work out with 2's complement? All right. So if you were to just take a couple more minutes here, if you were to kind of summarize your findings in the paper, because all 3 of these approaches are viable at some level, right? Is your opinion that sign and magnitude and 1's complement, was that a failed experiment, or was that a necessary evil, if you will, that lead us to the need for 2's complement?
Mostly daily regular systems, the 2's complement was well preferred compared to the signal processing. The 1's complement is still used in the real world. I read some documents.
Okay.
We're still using for the signal processing.
But 2's complement certainly came out afterwards, right? 2's complement is the result of 1's complement and sign and magnitude having weaknesses. So that's why we came up with 2's complement.
Oh, 1's complement is for 2's complement is literally using 1's complement.
Yeah, it's a superset.
Yeah, just to overcome the single negative 0 extra bit pattern issue, so that the 2's complement becomes famous. Still, the 1's complement is useful in the signal processing.
Oh, sure. I mean, well, as he just said, 1's complement is required for 2's complement. It gets its own instruction, right? You might want to knot things for other reasons, but it does get its own instruction in the 8086 assembly language. Okay. I guess let's not beat a dead horse there. So let me jump over to, what's up? All right, so we're going to, actually, let's see. So I put it up on the website. How many of you happen to install the MU8086 emulator? Right, two and a half people? I didn't officially assign it, I just gave you the things for it. So we're going to be using a tool in here called MU8086. Kind of looks like this guy. I'll just give myself a blank. All right, so idea here is that I'll just do a quick little thing. Sometimes they get very violent. I wonder what's up with that. What? I didn't break anything on purpose. Let's try to launch that again. It's technically the first time I did a new file. Is it just like locked?
Did you register it?
Did I do what?
Put in the registration code. You don't need one.
Shouldn't need one for 30 days. I think there is a registration code eventually.
Wow. Depends where you download from.
Here, let's go to one
It
of
worked
there.
earlier, didn't it?
Yeah.
I think it's just 'cause it's the Mac. Is there like a read-only button or something?
You gotta go deep in the settings. Let me play.
That's really interesting, actually. All right, so what's this buy registration key? Let's see what this brings up. It's limited to a it's limited to a 14-day free evaluation period. We're within that, so that's not the issue.
Yeah, you did it last week, didn't you?
Actually, I just did this one this morning.
So you did it
I did it on my other computer last week.
last Tuesday or Thursday when you were in class? You started on that, didn't you?
Yeah, but I didn't finish installing this thing until this morning, so I'm on day 1.
You know, they make those really easy to open.
Because he splatters it all over his laptop. All right, let's give that one more shot. Oh, here, I bet you this is it. That's it. I already had.
open.
Yeah. Once in a blue moon, old Alex is right. It was already open from earlier. Yeah, he says, well, maybe you have something open in the background.
No.
No. All right, so just kind of give you an idea on how this guy works. Can you see that? Is that big enough?
I'm blind, so
Would you be able to see it if it was like 4 times bigger? Probably
no.
not.
I gotta go get my
What about, can you see it? Or is it too small? All right, well, the question was, can I make it bigger, and whether I should put the effort into making it bigger. That's really what I was getting at there. Let's see.
options?
Set font.
What is that?
Monster.
So font 6 is not.
Just change
Go
it
to
into,
font 66?
Did you do anything? What did he do?
I tried to change it.
Literally as
It's like
large as
font is
possible.
in Chinese.
Oh boy.
They have Vietnamese?
Did you click OK last
Needs
time?
Kong?
Thought I did.
Do they have Vietnamese?
Is there a save? Don't save.
Unassociate.
Maybe highlight it and try it.
Oh, I could change background color. Well, I can
Yeah,
attempt to.
Pink. The holy color of the Amish.
Here, we'll try
Don't leave
18.
anything in 200.
How's he doing in Sheboygan?
He's dead.
Oh, is he? Did he go back to his people? Or did he?
No, he was.
No, he's not in Effigy.
He's Amish. He got,
It's not.
actually, executed as a witch.
Oh, burned him with the stake? Yep.
It's not like remembering.
Burned with the stake.
That's weird. Yours gives you a lot of options for font. The Windows.
Oh, hold on. I'm thinking
You
that.
gotta restart it.
Yeah.
Mine only gave me like 5 options. Maybe because you had something open in the background.
It's got to be it. All right, so let's close that. Let's close this. That's fine. We'll just save that. And let's reopen it. Recent files. That's not any bigger.
Windows is way better.
All right.
Oh,
Well,
here we go to the. Oh.
this is just the way it is.
Alright, okay.
So
Can we do the mouse zoom thing so it like pretends to scroll?
I don't think that works out here.
You just hold control and then scroll.
This
Command.
command.
Ooh, that's help. Just a Windows or a Mac thing where you can just like.
Yeah, oh no.
Isn't that running like a Windows
Yeah, this is running as a Windows emulator
on that?
on the Mac. Yeah.
That's just download parallels or something.
No, we're fine. Oh, zoom. Can I zoom it?
That.
Nailed it.
That's bigger. Yeah, it's definitely.
It's way bigger.
It's definitely bigger.
Is it a font problem?
Well, mine changes right away.
Which font are you using?
Well, I switched it to.
Do you have other things running in the background? Semi-serious question.
Ah, it was the font that was the problem.
Go bigger.
I can. No. Zoom out. There we go.
That's a little.
But bigger would still be better.
Oh yeah. Did you change it to the typewriter one? Make it really black too.
I hate you people.
I wasn't joking.
Okay, we can all see that?
You can see, but
Everybody can see that. All right. So for instance, if I move into BX100 and then I emulate this, it shows me. Oh, actually, I could change the font of this guy too. While we're at it, let's just do everything. Emulator screen, set font. Memory list. No, we're not going to use the disassembler.
You work with Cheat Engine at all? It gives you all the ASCII codes too. 000.
Really didn't make these guys any bigger, but that's fine. All right, so this allows me to step through it one line at a time. So if I just do single step, we just moved into the BX register, the value 100, which is a 64 in hex. So this is a decimal value I put in here. Here's the hex equivalent of that. So we'll talk about the various registers we have access to. But in any case, if you hadn't already installed this, there's instructions for PC and for Mac. PC takes 15 seconds. Mac takes about a half hour. Why wouldn't you have Xcode downloaded on a Mac? He's a programmer.
I haven't done it for iOS.
So why do you have a Mac?
I only started with Java and Android because that was the programming class I did.
Right, but why do you have a Mac?
Because it's pretty.
Okay, explain.
All right.
Okay.
That's
You just pulled the pin on
computer architecture class. That's a valid question. So why is Mac better? Now keep in mind, you're talking to somebody who's sitting up here with a Mac. Okay? And I'm challenging you on why a Mac's better.
The anti-Mac person,
Who uses a Mac?
yeah.
No, I like Apple. I'm not anti-Mac.
Well, you
I'm just realistic. All right, so to explain.
It doesn't get viruses.
Okay. So let's stop there. Why does it not get viruses? And I want to keep this in the context of this class because it is an important discussion.
Because people don't write viruses for it.
Yep, correct. Yep. So it's a small target, so virus writers tend not to target small targets, right? Okay, fair enough.
I think it looks cleaner.
Okay, so aesthetically, are you talking about the OS and the machine itself? Or both? Okay, fair enough. Fair enough. So I mean, I think most people would probably agree that Apple products aesthetically look better than. Then the argument is it worth the premium? Is it worth that price to aesthetically look better?
Do you at least have the memory or the storage capacity to boot it? Or no?
How much hard drive space do you have on yours?
128.
Well, you probably could as long as you don't have too many games and stuff on there. But okay.
Games on a Mac.
Well, I run all my World of Warcraft stuff on iMac and Windows.
In Windows.
Yeah, but that's an iMac.
Well, yeah, but mostly because the bot only runs on Windows.
You have that really crappy one in Mac.
Oh, I mean, the good bot, the correct bot, and you're talking about Pocket Gnome.
Yeah.
Doesn't exist anymore.
Really?
Yeah, they got shut down. It's like 90. It's not up kept. It's not kept up. All right. So anything else? Why? So the OS you think is cleaner, which I mean I think that's personal preference. Something that I ran into one time with a user is historically you hear the thing on the Apple side of things that people just say, oh well, Macs are easier to use, stuff like that. I don't know. I mean, if you're going to put Grandpa in front of a computer, I think he's going to have a better chance in front of a Windows machine than he will in front of a Mac. A friend of mine who's not a techie said something along the lines of, on a Windows machine, you at least know where to start. You start where the start button is.
But once you put the applications, documents, and downloads in the dock, then
Well, fair enough, but who's going to put them there?
Who knows how to put them there?
Apple Genius, you can take the
How?
computer to every 3
Well,
days.
fair enough. So Apple does kind of give you the setup process where they'll say, oh, what programs do you use? We'll throw them all there. So I don't think that's a horrible argument that the OS is easier to use. I think that's more dependent on the user maybe. I think saying that the hardware itself is more aesthetically pleasing or better built or something, I think that's reasonable enough to say. So then the question is it worth the premium? So what else?
the OS upgrades were free. Windows 10 is free, but they tried to force it on everybody. And
Fair enough.
they tried
Yeah.
to gather information on
They stopped doing that now. What? Like forcing updates?
Yeah, it's not free anymore.
Windows 10?
Made it through. Still got 7 on my desktop.
Windows 10's free. It's a free upgrade for everyone that has.
I don't think
I
thought they were only
It was
offering
free
that
for a year though. Yeah, it cut off.
We got
You can still get it.
Yeah, we have a site when we have a site license on campus, so you can get it for free anyways. But
well, even if you did it.
yeah, I get it. Okay, so the way I've always viewed it. Do you have any other reasons, or is that?
Not off the top of my head.
The way I've always viewed it is so kind of piggybacking the let's say better built, nicer, put more effort into the casing, whatever, that kind of stuff. I kind of view a Mac as kind of like a Cadillac, and let's just say your de facto quote PC laptop or whatever as being like a Chevy. They're both cars, they'll both get you to work. Some Chevys are pretty nice Chevys, right? But at the end of the day, my argument for a Mac is if you're a technology person, buying a Mac with a big enough hard drive that you can dual boot is like getting 2 computers for the price of 1.7. That way you have a machine that you can boot into Windows for doing .NET stuff and World of Warcraft cheating and that kind of stuff. And then you also have the Mac side for doing Mac development. So really the reality is iOS development. I mean, that's the only real Mac development that people do. I mean, yeah, there's a Mac App Store, but the mobile App Store is a significantly larger marketplace than the Mac App Store.
I feel like though if you get like a MacBook though, you kind of have to buy into like the whole Mac everything though. Like once you buy into everything Mac or Apple at least,
Yeah,
Once you buy the iPhone and you buy the iWatch and you buy
yeah, your argument, you don't have to, but it behooves you to.
right,
Yeah, yeah,
it's kind of like everything just
It works if you have everything in the same ecosystem.
yeah.
Yeah, that's true. Fair enough.
I would say things true with like Android though. Is that
Well, and Windows. I mean, if you use all Microsoft stuff together, they work best if you use the tools together.
Yeah.
But yeah, so I mean, the true argument would be get the machine that's the right tool for you. You know, so like when I have folks come up to me and say, "What kind of machine should I get?" Like, well, what are you going to use it for? It's like, oh, I'm just going to check my email. Well, buy the cheapest laptop that you need that you can find. That will let you check your
email on the desktop.
Yeah. It's like, well, I need a bigger screen. Okay, so then get one of those all-in-one things that has a giant monitor on it. That's the cheapest one of those that you can find.
it's like a 1084 resolution?
Yeah.
1024.
Right. Yeah.
I just want to see my emails in high def.
I need to see those pixels, those premium pixels.
Paxton needs to
All right.
see those all black letters.
So let me get us to a decent. All right. Let me get us. Shut up. Let me get us to a stopping point here. So okay. So we did two's complement. Okay. So I want to at least introduce a couple of documents here. All right, so something we're going to do tonight is, now how many of you, when you get a new computer, the very first thing you do is you open up and you read the entire manual?
100%.
Unless somebody,
Do computers still come with manuals?
I don't think so.
They're online.
I think there's like a PDF maybe or something or.
Okay, so this is from 1979. How many of you were around in 79?
79? That's a little dated.
How many of your parents were around?
you're an old man.
I know. Oh yeah, I Xerox this. This is my own copy. I probably do have an 8086 manual. Well, actually, it probably burned up in the fire in my dad's basement in his office. But
What was it like working with the
I never worked with those. ENIAC and back. Like, man, those gymnasiums were just so warm. The humidity. All right. So we're going to be looking at this sometime tonight after we look at this other document. But this is the user's manual for the 8086 processor. And as we walk through here, I just saw bipolar. The octal latch. I don't even know what that means. It doesn't sound healthy. Multiprocessing.
It's an adult word.
But down here they have diagrams of like the bus system and things like that. And farther down they actually show us the breakdown of registers. That's what we're going to be more interested in. Yeah. Okay, so what we're going to look at right after we take our break, so we'll take a break here in a second. Let's just get a review of this real quick, is kind of the structure of an 8086 assembly language program. And one of the things we're going to talk about is this idea of the data model. We'll talk about what that means, and then kind of how programs get put together. And then we'll look at some samples, and we'll start looking at some of the instructions that we can use this for. And at the same time, what we're going to start doing is we're going to start implementing a emulator of our own for an 8086 emulator, which is going to be the simplest of all emulators. But what we're going to look at it for is not so much being OS dependent. So the 8086 processor itself didn't necessarily have DOS in mind, right? We talked about this a couple classes ago. So these processors, they have a pile of resources associated with them. So the list of registers, that kind of stuff. And then beyond that, the operating system says, oh, I know where I'm going to look on that. I'm going to go and look in AH or in AL for, which system call you actually want to execute and that kind of stuff. And then I'll go and do it for you. Well, it would be difficult to, not impossible, but difficult for us to write a emulator that actually ran a assembly language program. because I mean, you'd have to map it to the OS and stuff like that. And it also doesn't do us any good. There's plenty of assemblers out there that help us. But what would be helpful is to understand how each instruction works. So we can implement each instruction on the CPU, the hardware instructions, in software, emulating it, and keep track of the values of registers and things like that. Okay, and what I think makes the most sense is to do this as, let's see, we have, most of us are Mac users, but who in here does not have access to a Mac? Convenient access to a Mac.
Well,
All right, so
I can steal Nick's.
we're doing an Android app. So we're going to do this as an Android app. Yeah, I wouldn't go to the lab. Why should I ask you to go to the lab? So we're going to make a small Android app that is an emulator, and we're going to add one function to it at a time. We're not going to build this monster thing, but what we want to do is we want to explore the various 8086 instructions through how they work. Okay, and get an understanding of the flags and things like that. So we'll start looking at that in more detail in the manual after our break. All right, questions, comments, concerns, bribes? All right, let's take 10 minutes.